साइलेंट पे है मेरा. I can't see myself. Hello and welcome to the Aakash BYJU'S JEE YouTube channel. My name is Atiullah and I'm back with another session on JEE Mission 2022. So before we begin this session, just let me know if you can see me properly and you can hear me clearly. Okay, give me a yes, give me a thumbs up so that we can get started with this session. Alright, folks coming in. Hi Mayuresh, how is it going? Hi Sanket. Hi Falak. Hi Captain Jack Sparrow. Right, the usual names. Very happy to see the usual names coming in. Alright, so everyone can see me properly. So let's get started with this session. Alright, so if you have been following us, we are doing these sessions to give you a boost in your revision. Okay, so the topic we have chosen for this session is center of mass and collision, which is generally regarded as a slightly difficult topic. Okay, the questions can be slightly tricky, but everything is conceptual, and if we get the concepts right, we can solve all the questions. Alright, so the usual format, I'm going to throw a question at you. So take out your notebook, take out your pen, and we are going to solve them together. Alright folks, are you ready? So let's get this session started. Alright, this is the first question coming up. Are you guys ready? Let's begin. So we have a spring which is compressed between two blocks of masses m1 and m2 placed on a horizontal frictionless surface as shown in the diagram. Now when the blocks are released, they have initial velocities v1 and v2. Now the blocks travel distances x1 and x2 respectively before coming to rest. We have to find out what is the ratio x1 by x2. Alright, so I hope the question is clear. So before we begin solving this question, as usual, let me know what is the concept we're going to use to solve this question. Right? Let me know what is the key concept involved in the question. Hi Savita, how are you? Hi Adhira, how's it going? How are you folks? Perfect. Alright, so if the question is clear, just quickly let me know what is the concept we're going to use, because all these discussions are revolving around the concept. We have to first break down the concept and then we are going to begin to solve the question. What is the concept involved in the question? Alright, obviously we are talking about it has something to do with center of mass, and Captain Jack Sparrow is absolutely right. There's something to do with conservation of momentum as well. Okay, so first let me know, when do we conserve momentum? Okay, when do we get the license to conserve linear momentum? Okay, that is the key part in the question. So unless we are absolutely sure that we can conserve linear momentum, we should not go ahead with it, right? Alright, so first some basic things. If I have to write the position of the center of mass, how do we write the position of the center of mass? Okay, how do we define the position of the center of mass? Suppose we have a particle whose mass is m1, so m1 r1 plus m2 r2 and so on, however be the number of particles, divided by the total mass m1 plus m2 and so on. Is that right? Now if we take a delta on both sides, okay, if we take a delta, the difference on both sides, then can we write it as delta rcm is equal to m1 into delta r1 plus m2 into delta r2 divided by m1 plus m2. Since there are only two masses in the system, I'm just considering m1 and m2. Okay, now what is delta rcm? Delta rcm is the displacement of the center of mass. So displacement of the center of mass is equal to m1 into delta r1 plus m2 into delta r2 divided by m1 plus m2. Okay, now we bring in the concept of conservation of linear momentum. Okay, so when can we conserve linear momentum? We can conserve linear momentum when the external force on the system is 0. Okay, and we can conserve linear momentum in components. For example, if the net force in the horizontal direction, net horizontal force in the horizontal direction is 0, so we can conserve linear momentum in the horizontal direction. If the net external force is 0 in the vertical direction, then we can conserve linear momentum in the vertical direction. So we can do it component wise as well. Okay, so if the external force is 0, then the acceleration of the center of mass is also going to be 0, because the acceleration of the center of mass only depends on the external force. The internal forces cannot affect the center of mass. Is that correct? So the acceleration of the center of mass is 0. Now think that we started. How did we start? We started when both the blocks were at rest. Is that correct? So we compressed the blocks. So at the time of release, both the blocks were at rest. Okay. So what does it mean? Does it mean that the center of mass was also at rest? Absolutely, the center of mass was at rest. And if the acceleration of the center of mass is 0, then will the center of mass move? The center of mass will not move. So we can say that the displacement of the center of mass is going to be 0. And if the displacement of the center of mass is 0, then what can we write? We can write m1 into delta r1 plus m2 into delta r2 is equal to 0. Is that right? So that is the concept we are going to use. Now in this block we can see that if we take the masses and the spring as a system. So what is our system? Our system are the two masses and the spring. Now if that is the system, is there any force, external force in the horizontal direction? Sure, there are forces in the vertical direction. There is m1g, there is n, etc. There are forces in the vertical direction. But are there any external forces in the horizontal direction? Now the spring is part of the system. So whatever is the force exerted by the spring is going to become the internal force of the system. And the surface is frictionless. The surface given to us is frictionless, which means there is no force, no external force in the horizontal direction, which means in the horizontal direction, the center of mass is not going to move, and hence we can apply this in the x direction. I'm calling it x. I'm taking the horizontal direction as x. So in the horizontal direction, we can conserve the center, the linear momentum of the system. Is that correct? Alright, so now let's go ahead and solve this question. Now another thing I want to ask you is that in the question, if you look at the question, it is given that they travel distances x1 and x2 respectively before coming to rest. Now how can we just assume that both the blocks are going to come to rest simultaneously? Can someone explain it to me? Okay, can it happen that one block has come to rest and the other block has not come to rest? Why is it absolutely necessary, and it is given in the question, that the blocks come to rest simultaneously? Can someone explain that to me? Can someone explain that to me? So we compressed it and then we released it. So obviously they're going to go away. They'll have some velocity, they'll go away. Okay, and after some time the blocks will come to rest. So one block has come to rest. Why is it absolutely necessary that the other block has to come to rest simultaneously? Can someone explain this concept to me? I'm waiting. Conservation of momentum. Arnav says conservation of momentum. Bang on, bang on. Okay, so if we take the initial condition, both the blocks are at rest. Okay, when both the blocks are at rest, then the linear momentum of the system is 0. So what is the initial linear momentum? It is 0. What should be the final linear momentum? The final linear momentum should also be 0. Okay, if the final linear momentum has to be 0, in that case, if one block is moving and one block is at rest, then the linear momentum is not going to be conserved. Correct? The final momentum will not be 0. That is why we are absolutely sure that both the blocks are going to come to rest simultaneously. Okay, perfect. So we have done that. So we have understood that, which means we can now solve this question very simply. Okay, let's say block M1 has moved a distance x1 to the left and block M2 has moved a distance x2 to the right. Now remember that displacement is a vector quantity. Okay, we are dealing with vectors, so the direction of displacements is very important. So what I'm going to do is I'm going to take the right direction as positive. Okay, my wish, I'm taking the right direction as positive, so automatically the left direction is going to become negative. Is that correct? So what am I going to write? I'm going to write M1 multiplied by the displacement. What is the displacement? The displacement is minus x1 plus M2, and what is the displacement? The displacement is plus x2. Okay, so we have written M1 into displacement of M1 plus M2 into displacement of M2, and this should be equal to 0. Because the linear momentum of the system is conserved, the center of mass does not move. Okay, so from here what do we get? From here m1x1 is equal to m2x2, and we get x1 upon x2 is equal to m2 upon m1, and that should be my answer. Is that right? Okay, so what will be the correct option? The correct option is going to be option A. Is that right? Okay, so is the question clear? Is the concept behind that clear? All the small concepts that we have talked about, is that clear? Now if that is done, then let me know about the difficulty level of the question. What do you think is the difficulty level of the question from 1 to 5? Okay, 1 being the easiest, 5 being very difficult. All right, what do you think about the difficulty level and why we are doing that? So that you understand. I want to take away the fear from you. Okay, I don't want you to fear JEE. I want you to take it head on. And I want you to understand the questions that come in JEE are not difficult at all. If you're good with your concepts, you're going to solve each and every question. All right, so obviously this question is going to fall in easy category as suggested by you guys. I'm happy that you find that easy. All right, so now let's move to the next question. Okay, so what do we have here? We have a thin rod of length L, and it is lying along the x-axis, and one of its end is at x equal to 0 and the other end is at x equal to L. Its linear mass density. What is linear mass density? Mass per unit length. Okay, so its linear mass density varies with x, varies with the position x as k into x by L to the power n, where n can be 0 or any positive number. So it is given to us that n can be 0 or any positive number. Now if the position xcm of the center of mass of the rod is plotted against n, okay, so we have to plot the position of the center of mass versus n. Which of the following graphs best approximates the dependence of xcm on n? Okay, so we have to tell which of the graphs shows the correct variation of xcm with n. Is the question clear? Hi Astha, good evening. How are you? Good to see you. All right, so let me know, is the question clear? Okay, now how do we proceed to solve this question? Okay, can someone give me any hint on how do we solve this question? Okay, so one of the end is at x equal to 0, the other end is at x equal to L. Okay, so what are we talking about? We are talking about the center of mass of a continuous mass distribution. Okay, these are not discrete point masses. This is continuous mass distribution. This is a rod of length L, and the mass per unit length of the rod is changing. It is not uniform. And what do we need to calculate? We need to calculate the position of the center of mass. So can someone tell me how do we calculate the position of center of mass for a mass distribution which is continuous? Can someone give me a hint? Right, so what we are talking about is the center of mass of a continuous mass distribution. Okay, now when we talk about center of mass of a continuous mass distribution, then we have to do a continuous summation. Okay, and when we do a continuous summation, what is it called? It is called the integration. Absolutely. So if we have to find the center of mass, and I'm writing it in terms of x, we can write it in terms of x axis, we can write it in terms of y axis, etc, etc. Okay, so what do? We break this rod into very small pieces. Okay, we break this rod in very small pieces. Let's say I'm taking a very small length of the rod dx at a distance x from the left end. Okay, now these we are going to find out what is m1x1. Remember, what is it? m1x1 plus m2x2 plus m3x3. Okay, so for this very small mass over here, first of all, we'll find the mass of the very small part. Then we are going to multiply it with the position. Okay, so what do we write? We write it as dm, the small mass, multiplied by its position. So what is the position? The position, I'm taking x equal to 0 as origin. So what is the position? The position is going to be x. And then we are going to integrate it so that we get the continuous summation of m1 x1 plus m2 x2 plus m3 x3 and so on. And then what we are going to do is we are going to divide it by the total mass. Is that correct? So this is going to give me the position of the center of mass, and that is my action item over here. Is that correct? Okay, so how do we proceed? First of all, we need to find out dm. Okay, what is dm? So dm is going to be the mass per unit length multiplied by the length. Simple unitary method. So dm is, we have to find the mass of this small part, so we will do mass per unit length into the length. Now mass per unit length is already given to me. For this position, where is the position? The position is at x. So for this position, the mass per unit length is given to me like this. So all I have to do is multiply it by the length. And what is the length? The length is dx. So this is going to become k into x by L to the power n multiplied by dx. Alright, so this is dm. Perfect. Now what we have to do is we have to substitute over here. Okay, dm into x. So this is going to become the integral of kx upon L to the power n, then we multiply it by x, and then we have a dx over here as well. And the limit of integration is going to go from where to where? The limit of integration, the x is going to vary from the left end, which is at x equal to 0, to the right end, which is at x equal to L. So the limit of integration is going to go from 0 to L. Is that correct? Okay, but we have a problem over here. Do we know the total mass of the system? Do we know the total mass of the system? We don't know the total mass of the system. But can we find the total mass of the system? Of course we can find the total mass of the system. So the mass of this small element is dm. Okay. Now if I integrate it up in the proper limits, within the proper limits, will it give me the complete mass? Will it give me the total mass? Of course it will give me the total mass. So I'm going to integrate dm to find the total mass. So this is going to become the integral of kx upon L to the power n, and then we have dx, and the limit of integration is going to go from 0 to L as well. Sir, will today whole chapter will be covered of center of mass in this session? Obviously we cannot cover the whole chapter, right? Because of the time we cannot cover the whole chapter, but what we are doing is we are telling you the most important topics, the most frequently asked topics. We're going to discuss the most important concepts in this chapter. Okay, so that's our objective. So all the important concepts that are required, that is going to get covered. So we have a session today, we have another session tomorrow on center of mass and collision. So in both these two sessions, most of the important concepts are going to be discussed. Alright, so we have come up with this. Now what we need to do is, obviously we need to integrate this. Okay, so let's do the integration. I need some space for integration, so I'm going to write it over here. So this is the integral of, let me go back and see, what is it? This is kx to the power x by L to the power n, then we have x dx, this is going from 0 to L, and then this is divided by k into x by L to the power n dx, and the integral is going from 0 to L. Is that correct? Okay, so what I can do here is, so there is an x over here and there is an x to the power n over here. So can I write that together? Right, so I can obviously write that together. So when I write that together, this is going to become x to the power n plus 1, and then we'll have divided by L to the power n. Is that correct? Alright, now this becomes a very simple integral which we can do very easily. Okay, so take out the constant terms. The constant terms, k is a constant term, comes out, and L to the power n is a constant term which comes out. So k upon L to the power n comes out, and then we have the integral of x to the power n plus 1 dx from 0 to L, and then divided by, similarly we can take out k and we can take out L to the power n, and this will become the integral of x to the power n dx. Is that correct? Perfect. So what do we do here? This gets cancelled, and then now let's solve for the integral in the numerator. So x to the power n plus 1 is going to become x to the power n plus 2 divided by n plus 2, and then we have to divide it by the integral of x to the power n is going to become x to the power n plus 1 divided by n plus 1. Is that correct? And the limit has to go from 0 to L. Is that correct? Okay. Now if we put the limits, what are we going to get? I'm going to rub this off over here. If we substitute the limits, what do we get? we'll put L first, so this becomes L to the power n plus 2 divided by n plus 2, and then this is going to become n plus 1 divided by L to the power n plus 1. Okay, so in the denominator we have L n plus 1 and in the numerator we have L n plus 2, so this is going to get cancelled. L to the power n plus 1 in the denominator and numerator will get cancelled and we'll be left with L. So what is the final relationship? The final relationship is that XCM is equal to n plus 1 upon n plus 2 into L. Is that correct? Are we clear with this? So I'm going to write it down over here. XCM is equal to n plus, was it 1 or 2? N plus 1 divided by n plus 2 into L. Now can you tell me which is the correct graph? We have found out the relationship. Now can you tell me which is going to be the graph? Remember, L is going to be a constant. So what are the variables here? The variables here are XCM and N. XCM and N. We have to plot between XCM and M. Okay, Jack Sparrow is saying you have taken out the fear of JEE. Absolutely, I'm absolutely happy that I've done that, that you are able to do that, and that's what we want to do. All right, fantastic. Suhani is asking, sir, why we divide these? Why we divide what? Can you specify? What are we talking about? What do we divide? What exactly are we talking about? Then I can answer that. Okay, now, so we have got what is the relationship. Can you tell me what is going to be the correct relationship? Okay, first of all, so whenever you have a function where you have problem that what kind of graph it is going to be, okay, then the most simple thing you can do is at least take 2 points. Take x equal to 0 and take x tending to infinity. You can substitute those 2 points and find out what is XCM. Okay, that is going to give you an idea that what are the points that are on the graph. Okay, so in this one, if I put n is equal to 0, okay, let's say if I put n equal to 0 here, if I put n equal to 0, then what is going to be XCM? XCM is going to be L by 2. Okay, and if I put n tending to infinity, let me write it over here. If I put n tending to infinity, then what is it going to be? Then this is going to give me 0. Can you, I'm sorry, if I put n tending to infinity, then this is going to give me L. Okay, infinity plus 1, infinity would be there, and infinity plus 2, infinity would be there. Okay, both those terms are going to get cancelled. Okay, so basically what are we saying? That if n is infinity, you can neglect 1 with respect to n. So this is going to become n divided by n into L. So when n is tending to infinity, what do we get? When n is tending to infinity, we'll get XCM as L. Okay, so which graph is corresponding to this result? Okay, so there is a graph A and there is a graph D. Graph B certainly won't be the answer. Graph C certainly won't be the answer. Can you see that? Okay, now out of these two graphs, what is it going to be? Okay, so in this situation, what do we see? There's a constant region in the graph. Okay, there's a constant region in the graph. Do you think that can happen? Whenever you are changing the value of n, the value of XCM has to change. Okay, whenever you are changing the value of n, the value of XCM has to change. You cannot have a constant graph like this. Okay, so graph D is showing me that there is some region of constancy. Is that possible? That is not possible. So what is going to be the correct option? The correct option is going to be option A. Is that right? Okay. So what did we learn over here? The first thing we learned was how to calculate the position of center of mass of a continuous mass distribution. Okay, so we took up a rod. Now you should go back and then revise if it is a ring, if it is a disc, okay, if it is a semicircular ring, if it is a half of the disc. Okay, so we need to know the position of center of mass for these bodies, which are the standard results, and also we should know how to derive them. Is that correct? Okay, so go back, write it in your concept checklist and revise that when you're done with it. Is that right? The second thing we learned over here was that even if you don't know how a function is behaving, you can at least substitute 2 points and find out approximate graph. Is that correct? Alright, so Suhani is asking in second step why we divide. Okay, let me go back. Okay, are you talking about this? Okay, so why do we divide? So this is the numerator and we divide it by the total mass. Okay, so what is center of mass? Center of mass is the sum of m1 x1 plus m2 x2 plus m3 x3 and so on, and then we divide it by the total mass. So that is why we had divided by the total mass. And what is the total mass? This expression over here is going to give me the total mass, because that is integral of dm. Okay. All right, so Tufail is asking how center of mass differs from 1 and 2. I'm not sure, Tufail, what do you mean by this question? If you can give me some more clarity, please, I can certainly answer you. All right, so we are done with this question. What is the difficulty level? The difficulty level, someone is saying 2 out of 5, someone is saying 4 out of 5. They get some mixed bag. Okay, so people who are finding it a little difficult, then you should certainly go back and practice these kind of problems where we have to find the center of mass of the continuous mass distribution. Okay, when you do that, again your fear is going to go away. Okay, perfect. All right, perfect. So now let's move to the next question. Okay, what is the next question? The next question is, a boy of mass 20 kg is standing on an 80 kg free to move long cart. Okay, so there is a free to move long cart and there is a person on top of it, and the boy has a mass of 20 kg. Now there is negligible friction between the cart and the ground. Initially the boy is standing 25 meters from a wall. If he walks 10 meters on the cart towards the wall, then the final distance of the boy from the wall will be. Okay, is the question clear? So we have a cart and the surface is frictionless. It is not going to provide, it is not going to give any friction. And the boy is standing, he is at rest initially. Then he walks a certain distance. Okay, what distance he walks? He walks 10 meters on the cart towards the wall. Walks 10 meters on the cart towards the wall. And then we have to find out what is the final distance of the boy from the wall. Okay, now my first question over here is 10 meters on the cart towards the wall. What is this displacement? What is this displacement with respect to? Is this displacement with respect to the ground, or is this displacement with respect to the cart? Okay, that is the key catch in this question. Can you answer this part of the question? Arnav says the displacement is with respect to the cart. Yes, because it is written in the question that 10 meters on the cart towards the wall. So what they mean is that this displacement of 10 meters is with respect to the cart, not with respect to the ground. If it was with respect to the ground, it would have been a very dumb question, wouldn't it? So the boy has moved 10 meters with respect to the ground. Then what will be the distance from the wall? It is going to be 15 meters. Obviously, that is going to be a very dumb question. So what they mean over here is that this is the displacement with respect to the cart. Alright, so Sohani says, conservation of momentum use करेंगे? बिल्कुल करेंगे. बिल्कुल conservation of momentum ही use करेंगे. Absolutely, you're absolutely right. Okay, now as we discussed, in the horizontal direction, are there any external forces? So what is the system? My system consists of the boy and the cart. Okay. Now, is there any external force in the horizontal direction? I'm not concerned with vertical direction because displacements are not happening in the vertical direction. I'm just concerned with the horizontal direction. Is that correct? Okay. So in the horizontal direction, there is no external force because friction is not there and there are no other forces. So in the horizontal direction, we can conserve the linear momentum. Okay. And if we can conserve the linear momentum, the concept is still going to be the same. What is the concept? The concept is m1x1 plus m2x2 is going to be equal to 0 because the center of mass was at rest initially, the center of mass will be at rest finally, so the displacement of center of mass is going to be 0, which means I can use m1x1 plus m2x2 is equal to 0. What are these? These are displacements, correct? Now you tell me, if I'm writing this equation, what is x1 and x2 with respect to? Okay, what is x1 and x2 with respect to? Can you answer that question? In this equation I have written x1 and x2 are displacements, fine, but what are they with respect to? Can you answer that? Absolutely. x1 and x2 have to be with respect to the ground because we are conserving linear momentum from the ground frame. Remember, if we get onto the cart is going to be accelerated and then we'll have to apply a pseudo force, and then conservation momentum cannot be done from the cart frame. So if we are doing conservation of linear momentum, then it has to be from the ground frame. So all the displacements we have to write in the ground frame. Is that correct? Perfect. Okay. And then we are dealing with displacements. So when we are dealing with displacements, we have to deal with them like vectors. Okay, we do not want to make the noob mistake of treating them as scalars. Okay, usme we have to be very, very careful. Okay, so when I'm dealing with vectors, what I'm going to do is I'm going to assume a direction as positive. So the right direction I've assumed as positive. So obviously the left direction becomes negative. And now I'm going to assume displacements. Okay, I'm going to assume displacements. So this boy has moved some distance. This boy has moved some distance. Okay, this boy has moved some distance towards the left. Okay, I'm calling that x1. Okay, and then obviously the cart is going to go in the other direction. Okay, because boy is going to push the cart towards the right. So the cart is going to the other direction and I'm calling that x2. Okay, now this x1 and x2 is in what frame? It is in the ground frame. So I have to write these displacements from the ground frame. Okay, now let's substitute. m1 into, now you tell me what should I write? Okay, so x1, hang on. Okay, so I'm going to write it, I'm going to make it a little simpler to understand. So I'm going to use small x and I'm going to use capital X. Okay. This small x is with respect to the cart. Okay, so I'm writing small x with respect to the cart, and then capital X is the displacement of the cart with respect to the ground. Okay, now I'm writing the displacement of the boy from the ground frame. Can you tell me what will be the displacement of the boy from the ground frame in terms of small x and capital X? Can you tell me? Alright, so this small x, I have written it in terms of the small x is the displacement with respect to the ground, and then capital X is the displacement of the cart with respect to the ground. So how do I write x? Okay, how do I write x? So how I'm going to write x is, so if I have to find the displacement of the boy with respect to the ground, okay, if I have to write the displacement of the boy with respect to the ground, then I have to write the displacement of the boy with respect to the cart plus the displacement of the cart with respect to the ground. Okay, simple relative motion equation. Okay, now displacement of boy with respect to the ground is equal to displacement of boy with respect to the cart. Displacement of boy with respect to the cart is x, but in what direction? In the left direction, so I'm going to write it as minus x. Plus the displacement of the cart with respect to the ground, what is it? It is capital X. In what direction? It is in the rightward direction. So this becomes minus small x plus capital X. Is that correct? Okay. So Sankhya, you are right. You are absolutely right. You are writing it as small x minus x. But we have to follow the convention. Okay. So I have taken the right direction as positive. So I'm writing the equation according to my convention. So if you had chosen it in the opposite direction, then your answer is absolutely right. Okay. But since I have chosen it in this direction, then I'm going to write it as minus small x plus capital X. Is that correct? Alright, so now we are in a position to substitute. So m1 into x1. So this is going to become minus x plus capital X plus m2 into x2. What is x2? x2 is capital X. The displacement of the cart we already know in the ground frame. So this is going to be equal to how much? This is going to be equal to 0. Is that correct? Alright, so from here what do we get? We get the value of capital X as m1x divided by m1 plus m2, and this is going to become, what is m1? The mass of the boy is 20, the displacement with respect to the cart is how much? It is 10, and then we have m1 plus m2. Okay, so this becomes 200 divided by 100, so that is how much? That is 2 meter. Okay, did I do any calculation mistake over here? Why do I feel I've done some? Oh, it's 25. I'm so sorry. I'm so sorry. Let me check. Okay, it's 10 meter. No, I think I've done the right calculation. Okay, so 20 into 10 divided by 20 plus 80, which is going to be 100. So this is going to be 2 meter. Okay. So 2 meter is the displacement of what? It is the displacement of the cart. Is that correct? Now let me go over here and show it to you in detail. Okay. Now the cart has moved by 2 meter and the boy has moved 10 meter with respect to the cart. Is that correct? So assume that the cart and the boy have gone towards the left by 10 meter. Okay. And the cart has gone towards the right by 2 meter. Is that correct? So what is the displacement of the boy with respect to the ground? Okay. With respect to the ground, the displacement is going to become 8 meter. Is that correct? 10 meter, he has gone towards the left, and then 2 meter, he has gone right with respect to the, along with the cart. Correct? So what is going to be the displacement of the boy with respect to the ground? The displacement of the boy with respect to the ground is 8 meter. Okay? What does it mean? It means when I rub this, all of this, okay, and the boy is over here, then it has moved 8 meter with respect to the ground. Is that the final conclusion? Okay, is that the final conclusion? That is the final conclusion. We have found what is the displacement of the boy with respect to the ground. Is that correct? Okay, what does it mean? Now, what is the distance of the boy from the wall? The distance of the boy from the wall is going to be 17 meter. Is that correct? Okay. So, what is going to be the correct option? The correct option is going to be option D, 17 meter. Correct? Okay, now quickly, give me the difficulty rating for the question. It is a very frequently asked breed of question. Okay, now the same question could have been asked in terms of velocity also. Okay, they could have said that the boy is moving with certain velocity with respect to the cart. Then find out what is the velocity of the what is the velocity of the cart, or they could have found out what is the velocity of the boy with respect to the ground, and they could have twisted the question here and there. So what we have done with respect to displacement, the same logic, absolutely same logic is going to be applied when we are talking in terms of velocity as well. Okay, the concept remains the same. The center of mass was at rest, it will remain at rest. All right. Okay, so difficulty rating of 3, I will accept that because this requires concept. Okay, you should know the concept of not just conservation of linear momentum, but you should know how do we apply it as well, and applying it correctly with the correct concept, with the correct direction, with the correct concept of relative displacement. All right, Shendhan is saying that the difficulty rating is 2.8 out of 5. Okay, I would love to see the calculation over here, how you have arrived precisely at 2.8. Okay, that will be some calculation, right? But I understand what you mean, and I completely agree that this question falls under moderate category, and if you are well versed with the concept, then it is going to fall in the easy category. So it's somewhere between easy to moderate. Alright, Shankya is asking relative velocity vectors में लिखना सीख लो and this would be a cakewalk. Correct, बिल्कुल सही बात. Relative velocity के terms में लिख लो and this would be pretty straightforward. Okay, the only tricky part was to write the displacement of the boy with respect to ground. That was the only tricky part. Okay, perfect. So this is done, and now let's proceed to the next question. Okay, it's a long question. Let's go through it. So we have two bodies A and B of masses m and 2m respectively, are placed on the smooth floor. They are connected by a spring of negligible mass. A third body C and mass m is placed on the floor. The body C moves with the velocity v0, or too many words, I'll explain it to you. Okay. So we have A, which has a mass of m, which have B, which has a mass of 2m, we have C, which has a mass of m. Now A and B are connected by a massless spring. Okay, done. And then what do we have? We have this block C, which is moving at a velocity of v0, and it is going to strike A. Okay, it is going to strike A. When it is going to strike A, then A and B will start moving. Okay, A and B will start moving, and if A and B are going to start moving, then you can understand that initially A is going to move faster than B. okay, because the impact has been on A. So A will start move faster than B, which means the spring is going to get compressed. And if the spring is going to get compressed, then we are saying that the velocity, okay, at the certain instant after the collision, the velocities A and B are the same, and the compression of the spring is x naught. Okay. Then we have to find out what is the spring constant K. So when the velocities of A and B become equal, then we are saying that the compression of the spring is x naught. So we have to find out what is the value of K. Alright, so Captain Jack Sparrow is saying ऐसे question पढ़ने का ही मन नहीं करता है. Can you give me a reason क्यों मन नहीं करता है? What do you find? Do you find this question very boring, or do you find this question difficult? What is it that makes you find this question not so interesting? Movement conservation. I'm not sure, SVM. Do you mean momentum conservation? Okay, Captain Jack Sparrow, yes, this question is only wordy it is just wordy. Okay, when I solve this question, you will see how easily we can solve this question. True, there are a lot of words in this question, okay, it is, but my experience is, the more words in a question, the easier the concept is. That's my experience. So don't get bogged down by the length of the question. Okay, generally the question is going to be long, but the answer may be very, very simple, and we are going to see that how easy this question is. Okay, perfect. So let's solve this. All right, so what is happening over here? Small m, and this is also small m, and C is moving with a velocity v naught, and it elastically collides with A. I think it is given in the question. It collides elastically. Yeah, it collides elastically. Okay, now if it collides elastically with A, what is going to happen? Can you tell me what will be the velocity of A after collision? So C is going to collide with A. Can you tell me what is the velocity of A just after the collision? Shankya is saying V naught by 2. Arnav is saying V naught. Alright, so first of all, we are talking about elastic collision. Okay, when we are talking about elastic collision, you should remember this is a very well-known result. Okay, so when two blocks of equal masses, okay, they do a head-on collision, equal masses, head-on collision elastically. If they do that, then the velocities are exchanged. Do you remember this concept? Do you remember this? So we have two blocks with equal masses, and there is an elastic collision. Then in that case, what happens? In that case, the velocities are exchanged. Meaning, if this has a velocity v naught and this has a velocity 0, then after the collision, what is going to happen? After the collision, this block will come to rest, and this block will move with the velocity of v naught. Is that correct? Okay, so you can solve it. The method to solve any collision question is you conserve the linear momentum, and then you apply the equation for coefficient of restitution. Velocity of separation upon velocity of approach is equal to E. You apply that equation and then you solve for it. But this is a question, this is a category of question, or this is a special case which is going to come very, very frequently. So you should remember it. Okay, so I'm saying it for the last time. You have two blocks of the same mass and there is elastic collision, then the velocity is going to get exchanged. Okay, B को A को C की velocity मिल जाएगी और C को A की velocity मिल जाएगी. Is that correct? What does it mean? It means that after the collision, A is going to have a velocity of v naught. Do you agree? After the collision, A is instantly going to have a velocity of v naught. Okay, and what will be the velocity of B? Velocity of B is going to be 0, because the collision, we're just talking about the instant after collision. Okay, just after the collision, the velocity of A is going to be v naught and the velocity of B is going to be 0. Okay, अब we can forget about block C. ब्लॉक सी का काम हो गया, ब्लॉक सी को वी कैन फॉरगेट, ठीक है. ओके, नाउ how do we proceed? Now what is the next thing we should do? What is the next thing we should do? Can you tell me what is the next step that we should follow? Okay, so we have a block A which is moving with a velocity v0. We have a block B which is at that instant at rest. They are connected by a spring. And then after that, how do we proceed with this question? Now it is given in the question that x0 is the compression when the velocities become equal. Is that correct? Okay, so what we can do here is we can take both the blocks and the spring as a system, and we can see that in the horizontal direction there is no external force. Okay, in the horizontal direction there is no friction, so in the horizontal direction there is no external force, so we can conserve the linear momentum in the horizontal direction. Do you agree? So what we are going to do is we are going to conserve the linear momentum in the horizontal direction. Okay, the final situation is going to be something like this. Okay, this final situation is going to be something like this. We have A and B, and it is said in the question that their velocities become equal. Okay, it is said in the question that their velocities become equal and the compression of the spring at that time is x0. Okay, so can we conserve linear momentum? Of course we can conserve linear momentum. What is the initial momentum? The initial momentum is mv0 because only A is moving, B is not moving. Okay, now this is going to be equal to m into v. The final momentum of block A is going to be m into v plus the final momentum of B is going to be 2m into v. Do you agree? So block A has a velocity v, block B also has a velocity v, M has a mass, A has a mass m, B has a mass 2m, so this is going to become mv plus 2mv. Is that correct? Okay, so this is going to become, we can cancel out m from both sides, so this is going to become v0 is equal to 3v, which means v is equal to v0 by 3. Correct? So we have the final velocities of the blocks. We also know what is the compression of the spring. Now what we can do? Okay, now what can we do? Now we can conserve mechanical energy. Okay, are there external forces doing any work on the system? Do you see any external force doing work on the system? If external force is not doing any work on the system, then we can conserve mechanical energy. Okay, so now let's go ahead and conserve mechanical energy. Shakya is saying पर एनर्जी कंजर्व करना पड़ेगा. हाँ, बिल्कुल करना पड़ेगा. एक कंप्रेशन ऑफ द स्प्रिंग की बात हो रही है, ठीक है, वेलोसिटीज की बात हो रही है, तो एनर्जी कंजर्वेशन तो करना ही पड़ेगा, ठीक है. बट वी नीड टू बी श्योर दैट वी कैन डू एनर्जी कंजर्वेशन. एंड हाउ कैन वी बिकम एब्सोल्युटली श्योर दैट एनर्जी कंजर्वेशन इज गोइंग टू हैपन? बिकॉज the external forces, they are not doing any work. Okay, if the external forces are not doing any work and the internal forces, there is no friction, there is no dissipative forces. Okay, so then we can conserve the mechanical energy. All right, so let's conserve the mechanical energy. So initially what was the velocity? The velocity was v0. So what is the initial energy? What is the initial mechanical energy? The initial mechanical energy is half m into v0 square. The initial mechanical energy is half m into v0 square. Block B does not have any kinetic energy and the potential energy of the spring is 0 because the spring is uncompressed. Okay, there is no elongation or compression of the spring. So this becomes the initial mechanical energy. Okay, what about the final mechanical energy? So finally what is the situation? The final situation is that block A is also moving with V, block B is also moving with V, and the compression of the spring is x0. Okay, so this becomes half m into v square. Okay, we have already calculated now. What is the value of v? v0 by 3. Okay, so we are going to directly substitute that. So this becomes half m v0 by 3 ka square plus we'll have half m, and what will be the kinetic energy of block B? It is going to become half into 2m. Mass of block B is 2m. Okay, so this becomes v0 by 3 ka square plus what is the compression of the spring? The compression of the spring is x0, so the potential energy is going to become half k x0 square. Okay, perfect. Okay, so what we can do is we can equate the initial mechanical energy and final mechanical energy. So this becomes half mv naught square, and from here what do we get? Or we can just cancel out all the halves. Okay, when we do ei minus is equal to ef, just cancel out all the halves. Okay, they are needlessly there. And so what we do, we get mv naught square, and then we'll have mv naught square by 9 minus this becomes 2m into v naught square by 9, and this is going to be half k x naught square. Okay, so what do we get over here? So this is going to become 3 v naught square by 9. We take 9 as LCM, and then what we are going to get? We are going to get so 9 minus 3 is 6, so 6 mv naught square upon 9. This is equal to, oh, half is gone, so it is only going to be kx naught square. Okay, so 3 2 times and 3 times. So what do we have finally? 2 v naught square upon 3 into m is equal to kx naught square. Okay, so this is the final thing that has come. And what do you have to calculate? We have to calculate k. So k becomes 2 v naught square upon x naught square, and then we have a 3 here and we have an m over here. Okay, is that clear? Is the question absolutely clear? Is there a calculation error? What is the answer? What is the answer? Let me check the answer. No, I think the answer is right. 2 by 3 m v naught square upon x naught square. I think the answer has come out right. Don't think there's a calculation error. You can check that again. Alright, so we have found out what is k. Okay. Now I'm going to ask you a question. I'm going to ask you what is the maximum compression of the spring. Now in this question, if I ask you the same situation, exact same situation, okay, I'm going to ask you what is the maximum compression of the spring. Can you answer that? So in the question it was given that when the velocities of both the blocks became the same, the compression of the spring was x naught. My question is, what is the maximum compression of the spring? X naught. Askar says it should be x naught. Any more answers? What should be the maximum compression of the spring? X naught. Absolutely. Absolutely. And this is a very important concept. Okay. Remember this. The maximum compression or elongation of the spring is going to happen when the velocities become the same. Okay. When the velocities, so initially A has a larger velocity, B has a smaller velocity. Okay. So what is going to happen? A is going to move faster than B. So the distance between the blocks is going to decrease. And at one instant, the velocity of both the blocks is going to become the same. Okay, in that case we are going to get the maximum compression, because after that instant B is going to move faster than A, and when B is moving faster than A, then the spring is again will start to elongate. Okay, so exactly at the time when both have the same velocity, then the compression of the spring is going to be maximum. Is that correct? Okay, and similar argument can be given when we are elongating the spring. In that case, the elongation of the spring is going to be maximum. Okay, so this is also a very frequently asked breed of question. So do remember this concept. Alright, so what do you think about the difficulty level of the problem? Quickly let me know. So option D is going to be the right option. Quickly let me know. What should you think about the difficulty level? Mayuresh is asking, is measure of how far the spring can travel before it gets damaged. Okay, so first, yeah, we can certainly answer that question, but we'll have to know that what is the maximum tension that the spring can take. Okay, so there'll be a maximum tension that a spring can take. So if we know that, we'll know what is the maximum compression or elongation of the spring. And if we know that, we can calculate that. Okay, that is not a problem. Alright, so 3 out of 5, 4 out of 5, that's okay. It's moderate, I'll put it in the moderate category. All right, let's move to the next question. So what do we have here? We have a piece of wood of mass 0.03 kg is dropped from the top of a 100-meter high building. At the same time, a bullet of mass 0.02 kg is fired vertically upward with a velocity 100 meter per second from the ground, and the bullet gets embedded in the wood. The maximum height to which the combined system reaches above the top of the building before falling is, okay? What is the situation over here? So we have a building which is, I think, 100 meter tall, right? The building is 100 meter tall. Okay, so there is a piece of wood, we are dropping it, and we have a bullet which is fired from the ground. And what is the velocity of the bullet? The velocity of the bullet is 100 meter per second. Okay, so what is going to happen? The block is going to fall down and the bullet is going to pierce the block, and after the bullet pierces the block, it gets embedded in the block. Okay, and once it gets embedded in the block, it will start going up. It will start going up. Okay, so what is it that we have to find out? We have to find out from the top of the building, how high does it go? So I'm going to call it H prime. Let's call it H prime. Okay, from the top of the building, how high it is going to go. Is the question clear? All right, so let's try to solve it. Now, the first thing we need to understand to solve this question is we need to know what will be the velocities of the block, and the bullet just before the collision. Okay, this is certainly collision, right? This is collision we are talking about. So we need to find out the velocity of the block and the bullet just before the collision. Why do we need that? So that we can find the velocity of the system just after the collision, right? We need that. Okay, how do we get that? So what do we have here? Let's say this distance, how much is this distance going to be? Is this distance going to be half gt square? Okay, so since you guys are in class 12, you guys are mature enough, you're not kids anymore, so I'm not going to write the equations of motion ekdam pura s is equal to ut plus half gt square. I'm not going to do that. Okay, I'm directly going to write the expression what is required. Okay, so this wood, it falls under gravity from rest. So what will be the displacement? The displacement is going to be half gt square. Do you agree? Let's call this x. So x is how much? X is half gt square. So what is this distance? This distance is going to be 100 minus x. Okay, so what will be the velocity? What will be the displacement? The displacement is going to be vt minus half gt square. Do you agree? Okay, s is equal to ut plus half gt square. You know how to manipulate this. So this is going to become 100t minus half gt square. Is that correct? So what do I have? I have x is equal to half gt square, and I have 100 minus x is equal to 100t minus half gt square. Is that correct? Okay, now from here what do I need? I need time. Why do I need time? So that I can calculate x and 100 minus x. Do you agree? Okay, so I need time. So if I need time, what I can do is I can add these two equations. So if I add these two equations, I'm going to get 100 is equal to half gt square and minus half gt square is going to get cancelled, and I'm going to get 100t, which means t is equal to 1 second. What does it mean? It means that the block and the bullet are going to collide after 1 second. Is that correct? The block and the bullet is going to collide after 1 second. Is that clear? Okay, I think that is pretty straightforward kinematics we have used. चलो आगे बढ़ते हैं. So can we find out what is the distance from the top? Okay, can we find that out? So that is going to be half gt square. What do I need? I need the distance from the top. Okay, so that is going to be half gt square. So how much is that? That is half into, or do I need that? I need the velocity. Oh no, I need the distance as well. Yeah, distance is also required because we have to tell from where it takes off, right? So let's find that. So that is going to be half gt square. Do you agree? So that is going to be half into g into 1 square, which is 5 meter. Okay, so what is this distance? This distance here is 5 meter where the collision happens. Okay, what is this distance? This distance obviously is going to be 95 meter. 100 minus 5 meter, 95 meter. So we have found out at which position this collision happens. Okay, now we need to know one more thing. What were the velocities? Can you find the velocities? So velocity of the wood, how much is that going to be? It is going to be v is equal to u plus at, which means this is going to be gt. So this becomes 10 multiplied by 1, which is 10 meter per second. Do you agree? Okay. Similarly, can we find the velocity of the bullet? So this is velocity of wood, and we want to find what is the velocity of bullet. The velocity of bullet is going to be u plus at. So u, and because acceleration is in the opposite direction to velocity, I'll write the acceleration as minus 10 multiplied by t. Okay, so v is equal to u plus at. That's what I'm doing. So 100 is the velocity in the upward initial velocity, and the acceleration is opposite to the velocity, so I'm writing minus 10. So 100 minus 10. So this is going to be 90 meter per second. Is that correct? All right. So I'm going to the next slide for clarity. Okay, I don't want to make it too muddled. Okay. So the velocity of wood comes out to be how much? It comes out to be 10 meter per second, and velocity of the bullet comes out to be 90 meter per second just before the collision, and it is going to be an completely, perfectly inelastic collision. Absolutely. Absolutely. Jack Sparrow is absolutely right. Okay, it is going to be a perfectly inelastic collision. How do we know that? Because the bullet gets embedded in the block. Okay, so then they are going to move together. So it is a perfectly inelastic collision. Okay, now how do we find the final velocity? How do we find the velocity of the combined system? Okay, so the bullet is going to get embedded in the block, and then will start moving together. Okay, can you find out what is the velocity of the combined system just after the collision? Can you find that out? How do we find that out? Center of mass. How would we use center of mass for this? Okay, so how do we find the final velocity of the combined system? That's my question to you. Conservation of momentum, right? Okay, I agree, conservation of momentum. Okay, now if you remember, we can only apply conservation of momentum when there is no external force. Do you remember that? Okay, we can only apply conservation of linear momentum when there is no external force. Now, on this system, is there any external force or not? Okay, if I take the wood and I take the bullet as my system, is there any external force on the system or not? There is an external force on the system. Which force is that? That force is gravity. Okay, so the gravitational force. Gravitational force is acting on the system. Is that correct? Now, if there is an external force on the system, then how can we conserve linear momentum? Yes, absolutely. Gravity is acting. There is an external force on the system. So if there is an external force on the system, how do we conserve linear momentum? How can we conserve linear momentum? Take ground also as system. Okay. So you are telling me to take Earth as a system as well. Okay. Now if you take Earth as a system, then Earth के ऊपर भी gravitational force लग रहा होगा किसी और का. So there will be 4 gravitational force on the Earth as well. Correct. So in that case, what will you do? Then if you're taking that system, on that system also there is an external force. Then what will happen? So my question is, and this is a very critical question, my question is, there is gravitational force acting. There is an external force acting. So in this situation, how do we conserve the linear momentum? Okay, so Askar is saying velocity of the center of mass. Askar, what you're saying is absolutely right. That is another method of solving the question. But when your argument is going to be that the velocity of center of mass is going to remain the same. That is your argument, correct? You're going to use that argument and you're going to solve that. And that argument is only going to hold if we can conserve linear momentum, if there is no external force on the system, correct? So both these methods have the same underlying crux. What is that crux? That if there is external force acting on the system, then what gives me the license to conserve linear momentum? Absolutely. So Arnav, I have taken the block and bullet as a system itself. Okay, that is my system, the block and bullet. But there is gravitational force. Gravitational force too is an external force. Then what do we do? How do we conserve linear momentum? So here we are in a fix, right? So we have to get out of this. Conservation of mechanical energy. Now, mechanical energy in this case is not going to be conserved for two reasons. Number one, there is an external force acting. Okay? So, you can take the gravitational force as the internal force, then you can conserve mechanical energy. But remember, when the block and the bullet are colliding, then the block is going to exert a force on the bullet and it is going to change its velocity. The bullet is going to apply a force on the block, it is going to change its velocity. So the internal forces are doing work. There would be friction, there would be dissipative forces which are doing work. So you cannot conserve mechanical energy. Mechanical energy cannot be conserved in this case because there is internal forces which are doing work. Conservation of momentum for instant. Absolutely right. We're going to conserve linear momentum just before and just after. Okay, we're going to conserve that instantaneously. You're absolutely right. But that's the problem. When we are conserving the linear momentum, there is an external force. Ria is asking, in what condition can we conserve mechanical energy? So Ria, we can conserve mechanical energy if the work done by the system, work done by the external forces and the work done by the dissipative forces like non-conservative forces is zero. Okay? So how do we write the work energy theorem? We write the work energy theorem as work done by the external force plus work done by non-conservative force is equal to the change in potential energy plus the change in kinetic energy. Okay? So when the work done by the external force and the work done by the non-conservative forces are zero, then the change in mechanical energy is zero. Okay. All right. Okay. So this is a very critical concept and understand this. There's something called well-behaved forces and there's something called not so well-behaved forces. Yeah, it's fine to be confused, Prerna, and not to worry. And that's why I'm here to take away your confusion. Okay. So there are some forces which are well-behaved and then there are some forces which can act as impulsive forces. Okay. Now, when this collision is happening, the external force acting is the gravitational force. And the gravitational force is a well-behaved force. Okay, gravitational force is a well-behaved force, which means that its value cannot change instantaneously. Okay, gravitational force is going to be a constant. Okay, its value cannot change instantaneously, which means it cannot act as an impulsive force. Okay, it cannot act as an impulsive force. Similarly, spring force. Spring force is a well-behaved force. It cannot change its value abruptly. Okay, so it cannot be an impulsive force. Correct? Now, when we are talking about collision, then the forces between the blocks, the forces between the colliding bodies is so large that you can neglect the well-behaved forces. Is that right? When there is collision happening, the forces between the bodies is so large. That's an impulsive force. Impulsive forces are very large forces. They act for a very short period of time. So the impulsive forces acting are going to be very large. Okay, the impulsive forces acting are going to be much, much greater than the external well-behaved forces. Do you get that? External well-behaved forces. So in that case, you can neglect the gravitational force. Okay, in that case, you can neglect the gravitational force. So I'm going to give you a simple example. The example that we just did. I'm going to give you this example. Okay. So when we have a block which is moving with some velocity and it collides with another block and there's a spring over here. In this collision, there can be an external force applied by the spring. Okay. There will be an external force applied by the spring, but the spring is it is a well-behaved force. So it cannot act as an impulsive force. So in this case, we can conserve linear momentum. But suppose if I replace this spring by a rod, now the rod is going to apply a compression or a tension, and that can act as an impulsive force. So in this case, if collision is happening, we cannot conserve linear momentum. Why we cannot conserve linear momentum? Because there is an external impulsive force acting. Is that correct? So when there are external impulsive forces acting, we cannot conserve linear momentum. But if the external forces acting are non-impulsive, then we can conserve linear momentum. And that is the crux of this problem. Is that correct? So this concept clarity is very, very important. We take conservation of linear momentum almost for granted. We cannot do that. We have to be careful that the external forces are impulsive or non-impulsive. Is that correct? Now in this case, gravitational force is non-impulsive force, so we can conserve linear momentum. Okay, so let's conserve linear momentum. So mass of the wood is how much? Mass of the wood is 0.03 plus the velocity of the wood. Now the velocity of the wood is going to be downwards, so I'm going to take it as negative. So this becomes minus, how much? Minus 10. Okay, plus what is the mass of the bullet? The mass of the bullet is 0.02 kg. And then we have to multiply it by the velocity here, 90 meter per second. It is in the upward direction, so I'm taking upward as positive. So this becomes 90. Okay, simple conservation of linear momentum. Okay, so what I've done is, so this is the initial momentum. Okay, what is the final momentum? The combined mass is going to become 0.03 plus 0.02. That will be the combined mass of the system. And let's say it is moving up with the velocity v. So we can multiply it by v. So what we have done is we have conserved linear momentum. So from here, what do I get? From here, what do I get? I get, this is going to become 9 into 0.2, so 1.8 minus how much? Minus 0.3 divided by 0.05. So what is it? This is going to be 1.5 divided by 0.05. So this is going to be how much? This is going to be, I think, this is going to be 30 meter per second. Is that correct? I hope I have not made a calculation error here. So, right, looks like 30 meter per second. Is that correct? So I have found out what is the combined velocity. I'm going to rub this off. What is the combined velocity of the system? Now this is the combined velocity of the system, 30 meter per second. So can we find out how high is it going to go? So you can write it as S is equal to, and again I'm not going to tell you so much, u square upon 2g, right? If it has an initial velocity of u, then how high is it going to go? It is going to go u square upon 2g. So this becomes 30 into 30 upon 2 into 10, and that is going to give me how much? That is going to give me 45 meter, which means from this distance it is 45 meter. Okay, from here it is 45 meter. But we need this distance. So this distance is going to be how much? We have to deduct this distance. So this is going to become 40 meter. Is that correct? So what is the correct option? The correct option is 40 meter. Okay. So from the top of the building, we have to tell the distance. So that is going to be 40 meter. That is going to be my answer. Is that correct? Are we clear with this concept? Okay. So although the question was not difficult at all, the question was straightforward, I would say. A little bit of calculation, a little bit of kinematics involved. So the question was a bit lengthy, but not difficult at all. But my main objective with this question was to make this concept absolutely clear. Don't take conservation of linear momentum for granted. Okay, check and only then apply. Is that correct? All right. Perfect. Sir, please repeat. Which part you want to repeat? Okay, so I'm going to summarize what we did. So if there are external impulsive forces acting on the system, you cannot conserve linear momentum. If there are external non-impulsive forces acting on the system, then you can conserve linear momentum. What are non-impulsive forces? Gravitational force is a non-impulsive force. Spring force is a non-impulsive force, and other forces depending on situation can act as impulsive or non-impulsive. Okay, that is the crux of our discussion. All right, we have time for one last question. So let's quickly solve this. Okay, so what do we have? We have a simple pendulum. It is made of a string of length L. Okay, so again, I'm not going to, Ria is asking frictional force. No, frictional force can or cannot, may or may not act as impulsive force. Okay, it will depend on the situation. If the normal force on the surface is impulsive, then the friction is also going to be impulsive. If the normal force is non-impulsive, then friction is going to be non-impulsive. Okay, that's what you need to know. Alright, so let's talk about this question. So there's a pendulum, it has a mass small m, and there is a block which has a mass capital M. It is displaced by an angular displacement of theta naught and released. Okay, so it is released and then it is going to hit this block A. Okay, now when it is going to hit this block A will start moving, and this goes to a maximum angle of theta 1. Okay, this goes to a maximum angle of theta 1. So what do we need to calculate? We need to calculate what is capital M. That is the question. Is that clear? Okay, and the collision given to us is elastic. Okay, the collision between the bob and the block is given to us as elastic. Is that correct? Okay, let's try to solve this question. Now what is the situation? This is block A and this is, let's write it capital M, and then this is small m. Okay, so when it is going to be at the lowermost point, the velocity of small m is going to be horizontal. Let's call this velocity V0. Okay, let's call this velocity V0. Okay, and the velocity of the block is obviously going to be 0. So what is going to happen? A head-on collision is going to happen. Okay, and after that, what is going to happen? After that, capital M is going to move, let's say with a velocity, what should I call it? Let's say I call it V2. Capital M starts moving with the velocity V2, and small m obviously is going to start moving in the opposite direction. Let's call this velocity V1. Okay. Now collision is happening there. It's an elastic collision. It's an elastic collision. So what we need to do here is we want to find out this angle theta 1. Okay, we need to find out this angle theta 1. Now it is very clear this angle theta 1 is going to depend on what? It is going to depend on velocity. Is that correct? Okay. Now first of all, can we find what is V0? So when this bob comes and hits over here, can we find what is the velocity? Okay. To do this, what can we do? We can conserve mechanical energy. Okay. So we are talking about just before the collision. So we can conserve mechanical energy. So this height is going to be L cos theta naught. And this height, which height? This height. This is going to be equal to the length of the string. Okay. So by what distance? Let me make that more clear. Okay. So by what distance has the bob come down? The bob has come down by a distance of L minus L cos theta. Can you see that? Okay. The bob has come down. So this is L cos theta and this entire length is L. So by how much distance it has come down? It has come down by L minus L cos theta. Okay. Which means I can conserve mechanical energy. How do I conserve mechanical energy? mg, the potential energy has reduced by this amount. It has come down by this distance, which means the potential energy has reduced by this amount. So that is going to go into the mechanical energy. So that is going to become half m V0 square. Correct? So this m and this m gone, which means V0 is equal to 2gl into 1 minus cos theta under root. Is that correct? Is that clear? Perfect. Now if that is clear, then after collision, okay, when it comes up to an angle of theta 1, okay, when it comes up to an angle of theta 1, let's say it has a velocity v1 and it comes up till an angle of theta 1, again we can conserve mechanical energy, and exactly the same logic is going to be applied. Okay, so the height is going to be raised by L minus L cos theta 1. Okay, so when we apply mechanical energy over there, so then V1 is going to become 2gl into 1 minus cos theta 1. Do you agree? So what we have done is we have found out what is V0 and we have found out what is V1. Okay, and now we need to apply the concept of collision. All right, so let's start. So how do we deal with collision? Number one, you apply conservation of linear momentum. That is the first thing you do. And the second thing you do is you use the equation for coefficient of restitution. All right, so I'm taking the right side as positive. That's my choice. I'm taking the right side as positive. So what is the initial momentum? The initial momentum is mv naught. Okay, why mv naught? Because capital M is at rest, so the only linear momentum is mv naught. So this mv naught is equal to, what is the final momentum? Small m. What is the direction of v1? The direction of v1 is opposite, so I'm going to write it as minus v1 plus capital M v2. Is that correct? Any problem conserving linear momentum? I hope that is clear. Okay, next what do we do? The velocity of separation divided by velocity of approach is equal to the coefficient of restitution. And what is the coefficient of restitution? 1, because this is elastic collision. Okay, so velocity of separation is equal to velocity of approach. What is the velocity of separation? It is going with the velocity v1 in the left direction, and it is going with the velocity of v2 in the right direction. So what is the relative velocity? The relative velocity is going to be v1 plus v2. Correct? So what is the velocity of separation? The velocity of separation is v1 plus v2. Okay, and what is the velocity of approach? What is the velocity of approach? Capital M was stationary and small m was coming with a velocity v naught. So what is the velocity of approach? The velocity of approach is v naught. Okay, so both our equations are ready, and from this equation what do we need to find out? We need to find out capital M. Okay, we need to find out capital M, which means we can eliminate v2. So what do we need to eliminate? We need to eliminate v2 because that is not required in the answer. Okay, so we can eliminate v2 by multiplying it by capital M. So I have multiplied by capital M, and now I'm going to subtract. Okay, I'm subtracting equation 2 minus equation 1. Okay, so this is equation 2, this is equation 1. I'm doing equation 2 minus equation 1. Q eliminate. So we need to calculate capital M. Okay, so the objective of the question is to calculate capital M. Capital M निकालना है. तो V2 का काम है क्या? V2 का कोई काम नहीं है. तो we'll eliminate V2. Correct? Okay. So now we are subtracting it. So this becomes capital M minus small m into V0 is equal to capital M plus small m into V1, and this is going to get cancelled. So this becomes capital M plus m divided by m minus m is equal to V1 upon V0, or I think I wrote it opposite. V0 upon V1. Is that correct? Okay, so this is what we have got, and then we have to calculate it for capital M. So I don't have space. I'm so sorry about that. I don't have space. So if this part is clear, I'm going to rub this off so that I can do the calculation over here. Okay, so I'm going to rub the part above it. All right. So capital M plus m upon capital M minus m is equal to V0. We had already calculated V0, haven't we? So that was under root of 2gl into 1 minus cos theta naught, and that was divided by under root of 2gl. What was V1? It was 1 minus cos theta 1. Correct? Okay. So this 2gl and this 2gl is gone. But if you look at the options are quite strange. Okay, the options are in terms of theta naught and theta 1. What does it mean? It is given in the question that theta is small. Okay, it is given in the question that theta is small, so we can use some approximation. Okay, so how do we go about it? M plus m upon m minus 1. M is equal to, now 1 minus cos theta. So cos theta I can write it as cos theta naught. I can write it as 1 minus sine square theta naught by 2. Can I do that? Simple trigonometry. So what would I get? I'll get sine square theta naught by 2 divided by, and the under root of that. So under root को हटा देते हैं. So we have a square and we have an under root. So we can get rid of this under root. So this becomes sine theta naught by 2, and this becomes sine theta 1 by 2. Is that clear? And now what we can do is we can approximate. So because theta is small, we can approximate sine theta as theta. So we'll have m plus m upon m minus m is equal to theta naught by 2 divided by theta naught theta 1 by 2. So this becomes theta naught upon theta 1. Okay. Is that clear? So now what do we need to find out? We need to find out capital M. So what we'll do is we can use componendo dividendo. Yaad hai? We had learned sometime probably class 8. And I was thinking, when can we ever use componendo dividendo? But now I do realize that sometimes it makes our calculation much easier. Okay, so here we can apply componendo dividendo. So what we'll get is, we'll get 2m on top. So m plus m minus m, we'll get 2m on top. And then we'll get 2 small m on the bottom. And this will get theta naught plus theta 1 upon theta naught minus 1. Okay, so this 2 and this 2 gets cancelled, so this m comes over here, and hence this is my answer. Okay, Ria is saying I'm not able to think this way while solving by my own. That's okay, Ria. A little bit of practice and you should be there. Okay, and that's why we're doing this revision session, so that you know where you are missing. Okay, so go back and revise this, and I'm sure you'll be able to solve these questions. Alright, so that is my answer. What is the correct option? Then option C should be the correct option. Perfect. So that was the last question. Quickly tell me the difficulty level. 4 out of 5. I'll say, yeah, I'll give it to you 4 out of 5. I'll rate it somewhere around 3 because the concepts were well known. Okay, the concepts were well known. The application was a bit tricky, but yeah, that's okay. 3 or 4, that's perfectly fine. Alright, so what are you going to do now? You're going to go back, you're going to look at your concept checklist, whatever are the things that were not very clear to you, go back, revise, practice and repeat. Alright, that's all we have to do, and there is no reason to worry about JEE. There should be no fear about JEE. We're going to take it head on. Is that correct? Alright, so thanks a lot guys. Thanks for attending this session. There's such a interactive bunch of people. I absolutely love interacting with you because there's so much response that is coming. The interaction is two-way. The participation is amazing. I see the intent that you have. You want to learn, you want to get better. That's absolutely amazing, and that motivates me to come back every week and do this session. Alright, so I'm going to meet you guys very soon. Till then, keep practicing, keep getting better, have fun with learning, and thanks for watching.